Okay. We didn't go very far with the cereal proteins. We started talking about wheat. So what were the main, or what are the main protein fractions in wheat? Go ahead.
Globulins,
Yeah.
prolamins,
Yeah.
gliadins,
Gliadin is part of prolamin. Yeah.
albumin,
Albumins, yes. And there's one last one. Glutalins. Yeah. Well, so the fractions are albumins, globulins, prolamins, glutalins, and then glutenin is under glutel.
And sometimes.
Yeah, sometimes both are called under prolamin, but glutenins are high molecular weight prolamins. Yeah. Okay. So what gave prolamins their name? Proline gluten. Look at you, you're all energy and all one answer. Okay. High in prolamine and high in gluten. I think I mentioned it briefly. Since they're high in glutamine, what's the main interactions type of bonding that can happen within the molecule and intermolecular? High glutamine. What type? Like, is it hydrophobic, ionic, hydrogen bond, disulfide? Hydrogen bonding. There's a lot of hydrogen bonding that plays a very important role in the formation of the gluten. Why are gluten forming proteins that require an S not soluble at pH 6 to 9? They're not very soluble in water. Why? What did we say about their amino acid composition? They are low in. They're very low in. What amino acids contribute to charge? Oh, so acidic and basic. So they're very low in acidic and basic amino acids. Okay. What are the gluten forming proteins? Yeah.
glutenin and gliadin.
Yes. Glutenins and gliadins. Any questions before moving on? Are you ready for the exam that I'm going to put up today? Well, actually, I'm going to email only the graduate students the exam, and you have till Sunday midnight. Email me back. So you're going to type in your answers and you're just going to send it to me by email by midnight. I'm not going to put an assignment on campus. It's going to be via email. Okay. All right. So speaking of gliadins and glutenins, so the gluten forming proteins are the gliadins and glutenins, and within underneath each of those there are different types. So under gliadins, you'll have the alpha, beta, gamma, and omega. And then under glutenin, there are two categories. You have the high molecular weight glutenins, and then you have the low molecular weight. We look at gliadin. So gliadin is mostly a monomeric. That means it doesn't form a quaternary structure. It is monomeric. It has around molecular weight around 40, but it varies because there are different types of gliadins. So the alpha, beta, and omega, not omega, sorry, gamma, are the ones that I have cysteine. Omega lacks cysteine groups. Let's see. So the gliadins are usually responsible for extensibility of the dough, viscosity, and extensibility. So a high ratio of gliadin to glutenin will have a more extensible dough. And having a more extensible dough would serve best for a type of bread that is like flat bread or the pita bread, for example. that kind of application that you require it to extend and not be elastic, and you don't want it to shrink back. So gliadin plays an important role in the extensibility of your dough. So glutathione is polymeric, so it forms polymer via disulfide interchange. The monomers of glutathione are between 68 to 88. There are different monomers. We'll see them on a gel in a little bit. So there are three main ones that we normally see on a gel under reducing conditions. Otherwise, they form large polymers through disulfide interchange. We have two types of glutamics, the high molecular weight and the low molecular weight, and they are linked via disulfide interchange. Now, there's a lot of homology within the amino acid sequence. So it says here there are three domains. There is a central domain that is repetitive. So you have a specific sequence that keeps repeating in the middle region. But what is important that I want you to remember, don't necessarily remember the sequence, obviously, is that the cysteine residues, there are not a lot of cysteine residues, but they are located strategically on the N-terminus and C-terminus area. So that facilitates the intermolecular disulfide linkages. So they're not necessarily in the middle. In the middle region, there might be one cysteine residue, but most of your cysteine residue are going to be on the terminus. So, which makes it easier to form these large polymers with disulfide linkages. So this is typically when you run your gluten proteins on a gel, usually run under reducing conditions because your high molecular weight glutens will not migrate through the gel unless you reduce them. So we always run under reducing conditions. That's answered Coleman's question earlier. So these are the three different glutenins or high molecular weight glutenins that we normally see. And then we have a bunch of gliadins, but there's also the low molecular weight glutenin region. Just around 50 kb. And then you have the omega gliadins, and then the rest of the alpha, beta, and gamma gliadins are in this region between 30 to 45 kb. Yes.
To prepare before running this programming and deep programming and improve how we are extracting them for this discussion. Oh,
Next. Yes. Coming. It's all coming. All right. So, so when you're forming the gluten, we have the glutenins that are already associated with each other, the high molecular weight, low molecular weight, are bound via disulfide linkages, and then you have the monomer gliadins. So when we mix the dough with water and we start kneading, we are denaturing and allowing the gliadins to interact with the glutenins, and via different interactions. Hydrogen bonding is the first one that happens, formation of beta sheet, intermolecular beta sheets between the different molecules, and facilitating when they come in close proximity, facilitating the disulfide linkages to form this viscoelastic material. Okay, so this is just another illustration. So here's again, the gluten proteins are not soluble around neutral pH and a little bit below or over due to low amino acids that are acidic and basic. At lower pH and higher pH, they're moderately soluble, not so great either. And then this is where it's very important. The first interaction that happens when we're kneading and those proteins are interacting with each other, they start forming beta sheets of chemical structures. So they form beta sheets, they come together, facilitating disulfide energy, forming the macropolymer known as gluten. And it has the unique viscoelastic properties that we don't normally see in any other grain proteins.
Can I have a question?
Yeah.
So it's the combination of glutamine and gliadin that makes gluten, correct?
Yes,
So by themselves, they won't have that viscoelastic network.
I'll show you by themselves how they're gonna look like. You guys are ahead of the game. Okay, so back before some of you were born, in 2001, there was a very fascinating study. I felt like this is again a very basic research that is very valuable. Figured out that it's not just hydrogen bonding and disulfide linkages. They figured out that there is another type of covalent interaction that also takes part in the formation of the gluten, and that is tyrosine linkages. So tyrosine units, they can get oxidized and form a covalent linkage. So they kind of did a lot of trials to or experimentation to prove the formation of this dityrosine cross-linking. They did that, they confirmed the presence of dityrosine by mass spectrometry, but also they elucidated the mechanism that it is oxidation by having this peroxidase as a mediating enzyme. So peroxidase can be native, endogenous to the wheat flour, so it could be there. And in the presence of peroxidase and oxygen during the kneading process, this bonding is initiated. And then they proved it with the presence of reducing agents like cysteine or glutathione and antioxidants like VHT. And they confirmed that presence of reducing agents reduces the formation of dityrosine. So they said, okay, so it's not just hydrogen bonding and disulfide linkage, there's another mechanism of bonding that is happening. This is just a illustration of the different bonding, hydrogen bond, disulfide, dityrosine interactions. Okay, so now what's the role of glass transition in the formation of gluten? So basically, we need the temperature to be above the glass transition of a gluten forming protein in order for the dough to form, or in order for gluten to form. So we need to make sure we're above the glass transition, and it is dependent on the moisture content. Okay, so if we think about if we're kneading the dough at room temperature, we need about moisture content about 13% to cross the glass transition. Okay, we can get to a lower temperature at higher moisture content for glass transition. So, but it is a must to cross the glass transition temperature so that we go from glassy to amorphous, so that it is more pliable and flexible. Okay. So here is what I said is the formation of beta sheet is essential. So there is a couple of papers that I put reading material for you on Canvas. Then it's just for you if you want to learn more. Not going to be part of the exam or anything, but additional information that talks about the formation of beta sheet during gluten formation and the role of the beta sheet in the stabilization of the gluten. You've noticed this because all of you potentially have worked with dough before. So you put the flour, you add water, it first is sticky, right? And then the more mixing you do, the less sticky it gets, because water gets absorbed. And then you're starting to form this network, and then everything gets less sticky, and then you have a very nice viscoelastic dough, very coherent dough. However, extra mixing is going to cause the release of water, and then the dough becomes viscous, not viscous, sticky again. So you need to know how much to mix to get to that dough, that the consistent dough, viscoelastic dough, but over mixing will cause loss of water, and the loss of water will cause stickiness. Okay. So if you have anybody did farinograph before? Yeah, did you notice over mixing what it does? Yeah, so if you not familiar with the farinograph, it's a rheological instrument where you put your flour, you put your water, and then it mixes it for you, and it gives you, I'll show you later, a graph. It graphs the strength of the dough, at where in time you reach the maximum strength, and how long the dough stays strong before it falls apart. Yeah. Okay. Yeah, so properties of the dough is, it has to be extensible, but also you want to have some resistance to stretching, so that you have some tolerance of the dough. So that's why you need kind of a balanced viscoelastic properties and ability to hold gas. This is very important when we are making loaf bread, because part of making your loaf bread is you get the dough and then you let it ferment, it rises, and the gas is entrapped. And similarly, when you put it in the oven and then you bake, you want the air cells to form, and you don't want them to escape so that the whole system collapses. So are you familiar? Well, you're all familiar with the texture analyzer, but here you have a different ring. You call it a kefir ring. So you put it's like, I don't know, something that you would stick you hand your dough, and then you pull up. It kind of pulls your dough up. And then what happens here is you record the strength of the dough, like how much force it took to pull it. And then also you measure the length, how far you were able to extend it before it breaks. So that gives you an idea about the extensibility and elasticity of the dough. So the elasticity is based on the strength, how much you can extend before it breaks. And the extensibility is how long that dough can go before also it breaks. It's a cool rheological measurement. Okay. Sometimes we enrich the flour with some additives. So what happens if we add the reducing agent? What happens to the elasticity of the dough? It reduces the elasticity. So if you have a very strong gluten forming proteins, so if you have really high glutenin to gliadin ratio, but you really want extensibility, you're making pita bread. So you might want to reduce that strength by adding reducing agent. Sometimes you do the opposite. We add ascorbic acid sometimes to the flour. What does ascorbic acid do? It oxidizes. So ascorbic acid in water acts like an oxidizing agent. So what it happens then, we enhance disulfide interchange, we enhance elasticity. That we can do when we have a little bit of a weak flour in terms of high gliadin to glutenin ratio, and then we need to make a loaf bread. So we need to enhance the elasticity, the structure, the rise, the ability to hold the gas. Thiol blockers, these are chemicals that would block thiol groups. That means we prevent the formation of the sulfide linkages, so they kind of have similar effect to reducing agents. And we kind of talk about this quite a bit. How does gliadin to glutenin ratio impact the viscoelasticity? So higher gliadin, you have more extensibility. Higher glutenin, you have more elasticity. So you need that balance of viscoelasticity depending on the type of baked product you want to produce. So how would changes in the amount of high sulfur gliadins affect dough? So we said alpha, beta, and gamma gliadins have cysteine residues, whereas omega gliadins does not. So if you have more of the alpha, beta, and gamma, and less of the omega, you have better intermolecular disulfide interchange between gliadins and glutenins. So you have better viscoelastic properties. All right. So this is to answer Brittany's question. Okay. What did I work on as a master's student? I broke apart the gluten into different units, different gliadins, different glutenins, 9 different fractions. And then I rebuilt the flour with different gliadins to glutenin ratio to determine the impact on baking of pita bread. So that's what I did for 2 years. Anyway, but if you have only gliadin and you try to make a dough, this is what looks like. Very, very viscous and extensible and doesn't have much of elasticity. If you try to make a dough with glutenin, you don't have extensibility. It's very, very elastic, very, very strong. You pull it very hard to pull, it does not extend. When you have a combination, obviously, you have a very nice, extensible, viscoelastic. So it is elastic, it's extensible. So you have that, that different effects. And then the fractionation and reconstitution experiments. So, for example, I took the flour, I broke it into starch and different protein fractions and lipid. And then I reconstituted the flour in different ratios of gliadin to glutenin, and then studied the viscoelastic properties, lots of farinographs, lots of baking, determine the impact of changing that ratio on the dough characteristics and on the baking characteristics. So we learned a lot from these types of fractionation studies. Extraction of wheat gluten. So there is a traditional way of extracting gluten from flour, and it is just take the flour, make a dough, wash the dough under water, and what happens is when you wash the dough, actually this person is doing it wrong or illustrating it wrong. If you just put the dough and put water, it will fall apart. You don't want to do that. You want to continue kneading the dough under the water. So you're going to continue working it so that you lose the starch, the water becomes empty. So the starch goes away, and in your hand at the end is gluten, is what is it's a very gooey, elastically thing. Then you can take that gluten, you can freeze dry it, and then you can characterize it, fractionate it into 9 different fractions, for example, like we did. But there is the better way of, this is the gooey gluten. There's a better way, obviously, to extract the different protein components and to run them on a gel. So you get the flour, you defact the flour, basically. And then you extract first with water. Sometimes we combine these steps because if I want to get rid of albumin and globulins and I don't want them, I just put water and salt. So salt solution, I can get rid of both albumins and globulins, discard the supernatant, and then take the precipitate. And if I just put isopropanol and BME and acetic acid all together, I can get both gliadins and glutenins as gluten-forming protein. They get solubilized, and then the palate is your starch and fiber material you discard. So this is one way of getting total gluten, we call it. And then you have that total gluten, and then you run it on a gel, and you see your different gluten proteins. But if we want to separate and study them individually, we take we solubilize with water first, we take the albumin. Then we take the pellet, solubilize it with salty water, and collect the supernatant, and that will be the globulins. But then we extract the pellet with isopropanol, and that gives me the column, the gliadins. So then I will take the supernatant, has the gliadins, we dry that gliadin. Then I'll take the pellet, and then I add BME and acetic acid for isopropanol. Then that's solubilizing now the glutenins that are not very soluble. You need to soluble break the SDS, break the sulfide linkages by reducing agent, and add acetic acid to reduce the pH to enhance its solubility. So basically, then with that, you get your glutenins, your gliadins, your globulins, your albumin, and then you can study them further. These are the, when we take the gluten as is together, gluten forming proteins, gliadin and glutenin, and run it on a gel, you will have the high molecular weight glutenins, and then the omega gliadins, low molecular weight glutenins, and the rest of the gliadins. So we have bread making quality is assessed based on the differences in gliadin to the segmentation. So the more elasticity we have, the higher the volume we get, the better retention of gas. Now, if I want pita bread, I want extensibility. I don't want my bread to shrink. I don't want it to be thick. I want it to be thin and spread. And when it bakes, it cuts open, and you have a really nice thin pockets. You can put stuff in them and have a very nice falafel sandwich.
And I think you should bake some pita bread so we can really learn about this.
I baked a lot of pita bread during my master's. Now, you know who bakes my formula? Cindy took my thesis, got the formula recipe, and she's the one baking the pita bread. She does a very good job with it. Okay, so very briefly, corn proteins. So in corn, the main protein is zein, and is represent about well, the majority of the protein is zein, protein. But in zein, we have the alpha zein is the major component. You have the alpha, beta, gamma, and I don't know what is that. Huh? Beta? Does it? Okay. Anyway, we don't care about all of them. Alpha is the main component of zein. It's very hydrophobic protein, very insoluble. You can't do much with it for any applications because of its poor solubility. Very high hydrophobic residues, mainly leucine, proline, alanine, phenylalanine. The distribution of secondary structure. If they are free from the protein bodies, whatever that means, then they can have better dope properties. And oftentimes they are mixed. In a mixture, they perform well. On their own, they don't form good dough structures. This is what happens if you want to bake just corn flour alone. It does not, without any assistance, it doesn't form well, it crumbles. So it's very hard to form a viscoelastic dough. Oftentimes you have to, it has a high glass transition. You have to perform the mixing at high temperature, relatively above room temperature. You can reduce that if the moisture content is about 20%. You can have 28 degrees being above the glass transition. Now, why doesn't it form a good viscoelastic dough? It lacks high molecular weight polymer, or in other words, glutatins. Huh? So when we say high molecular weight polymers, we mean glutatins. So it is high in regular polymers, but it is deficient in high molecular weight polymers or glutatins. So what happens to the structures? It fall apart. So when we make the dough, okay, we form some beta sheet structures, but those beta sheets are not stable. They're kind of not maintained over time, which causes the collapse of the structure because we don't have a lot of disulfide linkages. We don't have the high molecular polymer that adds stability to the dough structure. We form the beta sheet, but then the beta sheet is not stable over time. And then when we bake, the whole structure collapses. So what do? We usually add hydrocolloids to help with, the dough structure and the loaf volume and so on. So it needs help for it to function in a baked product. And also, you saw this example, it's also adding transglutaminase to help formation of covalent glutamate. Again, to enhance the structure of the dough and the ability to form relatively good bread. Now, I stole this from Lect. They are using at Motif, they are using corn to simulate cheese by enhancing the elasticity of plant-based cheese so that and the melting properties. So they found that corn polymer actually has good characteristics compared to other plant proteins in a sense that they have some stretching capabilities as well as melting properties that can simulate dairy cheese. Okay, now intermediate wheatgrass has been in our lives for the past 11 years, trying to make use of them, but what they are deficient in, they are deficient in high molecular weight glutamate. So here's this gel looking at different varieties of intermediate wheatgrass, and when we compare it to wheat, we can see that those high molecular weight glutamins are kind of lacking or not present. In some cases, not present, other cases there are, but at very low relative abundance compared to the ligands. They do have a very unique high molecular weight glutenin at around 60 K, just a little bit under 66 kilodalton. We found that through proteomics that the intermediate wheatgrass, they have 60 kD high molecular weight glutenin, so it's lower molecular weight than the high molecular weight glutenins present in wheat. So it's very unique kind of characteristics. Now, people might thought at the beginning, oh, so they don't have the allergenic component for gluten sensitivity or gluten allergenicity, but they do. Given the glycan that is present in there, they are not gluten free, so there's no benefit of using them for gluten free. So they don't function as the wheat, but still they are allergenic or they have gluten. So we look at their characteristics. We did studies looking at their secondary structures, and we found that they don't form as much beta sheet and they form more random parts. So the beta sheet was significantly lower, 100% in the wheatgrass, and you have higher random foil than wheat. So this tells us that they don't necessarily form the required beta sheet for stabilization of the dough, and they are deficient in high molecular weight, so they are low in disulfide. The side experience looked at differences, semi-quantitative differences in those fractions, the albumin globulins, non-functional, the gliadins, low molecular weight polymeric proteins, that means those, lieutenants, and the high molecular weight polymeric proteins or high molecular weight lieutenants. So when we looked at the distribution area relative abundance, so this is hard-red wheat, this is intermediate wheatgrass bulk from different varieties. So the hard-red wheat has slightly less gliadins, but significantly lower albumin and globulins. So we have more albumin and globulins, non-functional protein. And then we have significantly less high molecular weight polymeric proteins in the wheatgrass compared to wheat. And then when we did the graph, this is what the intermediate wheatgrass. So it reaches the 500 unit very quickly, but then the dough collapses also very quickly. Whereas the wheat, it reaches and it stays strong for a longer period of time. So it's basically a sticky mess in the farinograph and requires more water for it to form. Of course, try to make a bread out of it. This is what the bread looks like compared to wheat. It doesn't have a strength. It's very dense. You can see the crumb structure very dense. So it's not expand. You can make good cookies out of it. Cakes. So it's fine. They just worked on the recipe at the beginning when they started doing that. I had one of the faculty members that left us, but she did this effort. Her first formulation, when I ate it, like, oh, this tastes like a guinea pig chow. So like, what are you doing? And then over the years, they enhanced it, and actually it doesn't taste that bad. Yeah.
Is the bread like a pumpernickel, or it's not even like,
What's up?
is the bread similar to like a pumpernickel consistency?
I don't know what that.
bread.
It was, well, it tasted bad. It looked bad, bitter, dark, dense. It was very bad. But over the years, these are old pictures. If the wheatgrass folks hear me give this lecture, they'll be very unhappy with me. Now they do sourdough bread with it, and they mix 50% of the wheatgrass with 50% of wheat, and it's actually not bad.
Actually not bad.
Huh?
Actually not bad.
Actually not bad.
It's good.
All right, so that is cereal for you, and then I'm gonna not give the egg protein lecture. It's just not gonna happen. The last time I taught egg protein was in 2017. I have the lecture if you want it, but it's focus. Huh? The eggs? You're kidding. This is the first group that ever asked me about, okay, yeah, I can post it. For sure. Do you want, I don't know if I have a recording, but I have the slides.
Yeah, most of the slides.
I'll put the slides. Yeah.
This is why it's great. I know.
All right, I'll give you a break in 10 minutes. So stay with me for a minute. For 10 minutes. Your brain is full of gluten right now. Okay, guys, not break time. I lost the group. It's not a break time yet. No, the back. Huh? Oh, no, you can go. I was joking with you. But this is great.
But I see.
She left anyway. Okay. So. This map, where are we with the map? We're here. Look how much we covered. Wow, you guys are experts, everything. And now we are just tiny bit away from completing the map. Protein modification and how it impacts the structure and how the structure change impact the functionality. Okay, so let's see. Just a recap, I don't know why I have it here, but it's right there, okay. So globular native protein with low surface hydrophobicity. It will be, shouldn't say it better, should we say good emulsifier, a good gelling agent, good solubility? What? What do you remember?
Is this a question or a
Yeah.
statement?
What's that?
Are we supposed to answer the picture? It can have good.
Yeah, you're supposed to answer. Why?
It depends. No, I mean, like, if it's just the whole globular protein, I mean, it depends on.
So globular native protein with low surface hydrophobicity, it's telling you right there.
It's not gonna be good, it's like solubility.
It's not gonna be good.
All right,
It's
it's not gonna be. Not gonna be good then.
Coleman. Well, it's gonna be, have good solubility. Without denaturing it, it might not perform well here. And what about digestibility?
I don't know about reduced or reduced. It should be reduced.
It shouldn't be reduced, it should be low digestibility. Without denaturing, it's really hard for the enzyme to reach all of the binding sites. So usually, I think I gave this example, babies that don't have enough strong enzymes in their body, in their digestive system yet to be able to digest whey protein. So their baby formula is whey protein hydrolyzed for rehydrolyze a little bit.
This is why when they drink cow milk. So
They
are not
can
able to
digest it, yeah, yeah.
I just
Oh.
always thinking about it.
What protein is missing in human mother milk?
It seems very,
Be-
Beta-lactam.
Beta-lactoglobulin. So human milk doesn't have beta-lactoglobulin. That's why when the baby drinks cow's milk, they cannot digest it. Yeah. Mamas should breastfeed for 2 years.
2 years.
I did 2 years and 2 months. Yep. You didn't want to know that, Coleman, I'm sure. Why are you blushing? Okay. Denatured, partially, oh gosh, I'm unrecorded here. What am
It's all.
No, I'm blushing.
YouTube will know.
God will. All right, so when we denature the protein, what happens? That globular protein, what happens?
Opens up.
Yeah, it opens up. Now it becomes a better emulsifier, better gelling, improved digestibility, yes. And then now if we overheat, polymerizes, what happens?
Reduced overall functionality.
Yeah, reduced overall functionality, lower solubility, obviously, and reduced digestibility, because now we produce large polymers, and again, the enzymes will have a hard time digesting. Okay,
Can I have a question?
Yeah.
So if partially denaturing improves emulsification.
Yeah.
How come we never heat our proteins in lab and then run EC?
What do you do during EC though?
Share?
The shear.
Oh, so it's physical denaturing.
Yes, yes, yes. Okay. Protein modification. Why do we need to consider protein modification? Why don't we leave the proteins alone? Huh? Enhanced functionality, especially what type of proteins require flat proteins. All the proteins that you guys work with suck. So all of you are working to improve that protein functionality. Okay. So I gave this in the short course and I realized I didn't have that in the lecture, so I added this. Some of you might have heard me talk about this before, but what do we want from our proteins, especially plant proteins? What do we want from them? We want them to be soluble so we can replace whey protein in clear beverages, high protein, so we can claim high protein beverages. What would be the minimum concentration of protein to claim high protein beverages? 4.2, but 5 is that if we have a PDCAS of 0.8, then 5 grams per 100 is really 4.2 grams available. Then that's the minimum for FDA to claim a high protein source.
4.2?
4.2.
That's if it's gonna be that's one.
If you have PDCAS of 1, if you have 4.2 grams of protein, then yes, you will have them more available. If you have a PDCAS of 0.8, like P, then you need 5 grams. Yeah. Okay, so we want them to be soluble, and not just soluble, clear beverage, which is impossible for our plant protein at pH 3.4 to be clear, like whey protein. We want them to form gels like plant-based yogurt. We want the protein to form a nice network, to hold water, not to have syneresis. Okay. So we also want them to emulsify like plant-based cream cheese. We have a lot of fat and aqueous, and we want the protein in there to emulsify and have a nice cream cheese that is non-dairy. We also want to simulate meat. Gosh, we are demanding so far. So we want the protein to form fibrous structures like the fibro proteins in meat. So, and maintain also water so they are juicy, also not just fibrous material that is dry. Okay, so that's a lot. But why are plant proteins challenging? Why are they challenging? Look at their structure. So you have the little whey protein monomer that is very hydrophilic on the surface, and then you have your hexamer globular proteins such as 11S in pea or in soy. So it's large, up to 300 to 450 kilodalton compared to 18 kilodalton molecule. So 18 kilodalton molecule monomer compared to 300 to 450 kilodalton large quaternary structure protein. So very hydrophobic on the surface, so it associates to get maximum stability in aqueous by forming this hexameric structure. So it's not as simple, it is complex structure. Love-hate relationship, mostly hate with water. So not very soluble, especially if we heat process, we denature them even more, having higher surface hydrophobicity, forming large polymers, large aggregates. They're not going to be soluble in water. Especially that is when we denature them, we are exposing all of the hydrophobic material plus the surface hydrophobicity that originally they had. With increased surface hydrophobicity, less interaction with water, and with excessive processing, we get this mess of a protein. Large aggregates, insoluble aggregates, and not functioning. So there is a problem that we need to fix through a modification. So now you can take a break. Let's say 7 minutes break.
30 minutes.
7 minutes, stopwatch.
We don't know what our presentation looks like.
What's that?
So we did an update on what our for our class participation.
Participation, oh, yeah.
Oh, I think.
Yeah.
It's complicated.
Yeah.
Yeah, I think. Yeah, well, look, yeah, for the speech today. And good work.
I see that only few people is benefiting from the +5. You guys not doing the exercises, this is not just to get +5, but also to study the material and prepare you for the final. Oh, yeah. That's Yeah.
Water. So that you could calculate how much the outlay and actually get it on fire. No, it's point. Okay. So just do the math, if I want to go take the math. That's way more for the residents, so. Like, just come in there and yeah, yeah, so you have 100 now, how much, yeah, then it's, yeah.
Everybody's back in your seats, less than 7 minutes. What? What?
I was just saying, it's not so funny. Humans being, you have it lost it in the same spot.
Yeah,
Yeah.
and you all get quiet at the same time. Good. Yeah. Okay. Since you're all ready. Okay, so basically, they're complicated, they're hard to work with. Then we think about, okay, how can we modify their structure to enhance their functionality? So what are the different ways we can modify the protein? Go ahead, Ellie. Hydrolysis. So, hydrolysis belongs to what category of modification? Enzymatic. Enzymatic modification. Okay. Enzymatic modification. What else? Physical modification. Physical modification. Chemical modification. They are glycation. Yes, they are glycation. What else? What did we say? Enzymatic. They are physical, chemical. What are they? Blending? Huh? What did you say? Blending? Blending. Physical. Biotechnology. Yeah. Oh. So enzymatic, chemical, they are physical, biotechnology, breeding, and
I was wondering if we can consider Maillard reaction.
okay, it is a chemical reaction, but we don't use chemicals during the chemical modification. We use chemicals. Maillard reaction is a natural chemical reaction. Yeah, in literature, when you read it, sometimes they put it under chemical modification, and that's not. Because it is a natural chemical reaction. It is not, you're not using chemicals, phosphates or whatever, acetyl groups or anything to modify it. Yes.
Can we use ultrasonication for hydrolysis?
Ultrasonication is a physical modification. Ultrasonication can result in hydrolysis and break down the bonds. Yeah. So yeah, so that's why I don't say enzymatic hydrolysis, I say enzymatic modification, because with that you can hydrolyze blah blah blah. Physical modification, you can hydrolyze, you can form bonds, polymerize. It's under the category of physical. Physical means, so you use physical means to modify, to break bonds or to whatever. You use chemical means to modify, you use enzymatic to modify. Like that, make it clear? Okay. Now the question mark is, who knows what else is going to come up, right? So they might come up with something that does not belong to any of these chemicals. Can you think of anything that doesn't belong in any of these chemicals?
Co-plasma is bigger than.
Would, I don't know if we find it fall under biological or enzymatic, but like, fermentation.
Yes, I don't think. Like that.
Well, I mean, I guess.
Fermentation,
Yeah, right. It would- Yeah, sure,
right?
but yeah, it's not enzyme adding area.
Yeah, fermentation is questionable, but usually when you ferment, you're using the enzymes in those organisms to create new compounds or whatever. So, like the mycelium, to create mycoprotein, what do? You have the fermentation vessels, you put the feed in there, can be carbohydrate feed. And then the microorganisms ferment that and then produce protein, proteinaceous material. Yeah. Sometimes fermentation was under biotechnology, because if you think about the modification of the DNA of the microbes to produce casein, like in perfect day. Yeah. Okay, very good. So,
So the.
Yeah.
What about marriage license being chemical, do people differ on that opinion, or is it universal that marriage is separate? from chemical?
it's not universal, because it's like the same with water holding water binding and people using different terms, but it shouldn't be under chemical. From sound perspective, but people mix it up.
I don't know.
I'm not being biased to my own categorization, but chemical modification is you use chemical to induce a modification. In male reaction, you don't use any chemical. Protein reducing sugar, heat, natural reaction. It is a chemical reaction, it's natural. Okay. So, whatever we choose to do, the target is to improve functionality, but also we don't need to, we don't want to cause any nutritional damage or any physiological damage. So either enhance nutritional delivery or not mess with it. Sometimes deliver physiological benefits, like when we produce hydrolysate, we might increase the production of bioactive peptides, for example. Okay, so whatever we do, though, whatever we choose to do, it has to be safe. So we have to make sure that whatever it is we're doing, we're not generating by compounds that could potentially not be safe. Okay, so the idea of chemical modification is we want to change the charge. Either we decrease the net charge or we increase the net charge, decrease or increase hydrophobicity or hydrophilicity by adding, if we want to increase hydrophobicity, we can add long chain of anhydrides or hydrocarbons. If we want to increase the polarity, we might be adding small molecules like carbohydrates, small carbohydrates, or charged molecules that would add to the net charge. Sometimes we want to increase size by inducing cross-linking, adding reagents that will enhance covalent interaction, such as inducing methylation, adding a thiol group to the protein. Sometimes we do acid hydrolysis or alkaline hydrolysis to break the protein into smaller molecules. So, of course, these are your general functional properties that will be impacted by the chemical change. So, chemical modification has advantages that it will give you a desired outcome. It's very easy to implement, it's not expensive, but it has a lot of disadvantages. It's not targeted. So lack of specificity, not all side groups are reactive in chemical modification. we might change the amino acids into metabolites that could be toxic. We might reduce digestibility of the protein, so deterioration of quality. And some of these modifications can be reversible. So the reaction happens and it can be reversed. So then you lose the, obviously, the intent of it. So there are a lot of different chemical modification. There is a chapter that I have on Canvas for you. So I'm just going to highlight a few of them. So modification of amino acid, I don't know why I have it in last. Okay, so modification of amino groups. So within the amino acid itself, the amine group is the reactive, not the R chain, not the carboxyl group, the amine group. So there is a category called acylation. Under acylation, we have acetylation, so we add acetic anhydride. This is what I meant by adding a chemical. So we add a chemical, acetic anhydride. This chemical is going to react with the amine group of lysine. So the amine group of lysine under neutral conditions is going to be +1. So when you block it, you're actually increasing the net negative charge of the protein. You're not increasing the negative charge per se, because we are adding a compound that doesn't carry the charge. We are just, so there is no charge of this compound. You're blocking a potentially positive charge. So you're basically increasing the net negative charge, which can affect enhanced solubility potentially at a particular pH. And in some cases, it has been used to enhance the emulsifying property in case you have a lot of hydrophobicity on the surface. Increasing net charge can help with the emulsification activity. So this is the finding of this reaction or change.
Can you say that again? So we're not changing the charge, we're just blocking it?
Yeah, so you're not adding a group that carries a charge.
Okay.
So you're not adding a charge to the protein, you're blocking potentially a positive charge. So your net negative charge will increase. Okay. Now, the next one is actually adding a negative charge. So this one is succinylation. So here you're adding succinic anhydride. So that is the chemical that you add. It also mostly reacts with glycine as well as other amino acids. What happens is, again, it reacts, let's say, with the amine group. It's the amine group reaction. And in this case, you form, in this reaction, you get a negative charge here. So you're blocking a positive and adding a negative. So you're increasing the net negative charge more than the previous reaction. So here we see significant increase in solubility and thermal stability because we're having more charge now. And there has been studies that show that emulsifying and foaming capacity will be increased for some proteins as well. All right. So this is the comparison. Both are under acylation, acetic anhydride and succinic anhydride side by side. The disadvantage is they react with lysine. Okay, so lysine is essential amino acid, so you have nutritional loss, and also it has been shown to have reduced digestibility.
Do they use it in like industry or anything like
In the US, chemical modification is not approved, but in different countries, I don't think in Europe either. In Asia, yes. What? What did
She said
you?
interesting.
Yeah. You know, it's funny because when I worked at Cargill, they have Cargill North America, they have Cargill Europe, and they have Cargill China. Cargill China, they do phosphorylation, glycosylation to improve protein ingredients. Cargill, but Cargill in North America doesn't do that. So it is really funny that way.
Over the summer at Dill, when we were extruding, we would have cargo from like America and cargo from China,
Yeah.
like key isolate or something, and one would work well, and then the one from China was just like terrible. So I wonder if it's because they are able to use like different like methods on it,
So the China was terrible or better?
worse.
I don't know what they did, but yeah. Oh, the other thing that also when I was working there, we were working, trying to get a joint venture with Puris. And we wanted to help guide them in the way they produce their pea protein isolate. So one of people I used to work with, a researcher, went to China to observe how they do the production in China compared to here. And then she told me they solubilize the pea protein at pH 10.5. And I was like, oh dear, no wonder. It's just, it's going to be super oxidized, it's going to be not functional. And yeah, because they want to maximize how much protein they can get out. No. Increase the yield, yeah, and
If
reduce the
they're-
loss.
If they're running a protein functionality, wouldn't they care about that, instead of just the yield?
Well, I don't know, money talks, you know, you have more protein, yeah. It's interesting, different countries, different regulations. All right, so disulfide, sulfide groups and redox reactions. So chemical reactions that induce changes in disulfide interchange or cause disulfide interchange or reduction. So adding a reducing agent. So glutathione, mercaptoethanol, we do that mostly for analytical purposes. So that interference usually is mostly for, you know, analytical purposes so that we can look at them separated on the gel. But in industry, they can use sulfides. Yeah, so they can use sulfide as a reducing agent. Sometimes they add reducing agent to enhance extraction as well. So adding sulfide during alkaline extraction enhance solubilization of proteins that otherwise are large polymers, disulfide interchange. So that can be used. Sometimes also adding sulfide to the formulation can also help with reducing disulfide interchange. So for whey, for example, has two disulfide linkages within the molecule. If you reduce it to enhance flexibility and movement to the interface. So you found that, oh, they can enhance foaming properties. Use of sulfide is a reversible modification because once you reduce disulfide bond, you are creating SH groups, free SH groups, so that can act as inducing disulfide interchange. So that's why it is not always, the concentration is also very critical, how much sulfide you can add. Sometimes adding a specific concentration can be critical, causing the opposite effect, causing polymerization rather than just reduction of disulfide. So it is tricky, not easy to work with. Ascorbic acid, we talked about that. It has many functions in food applications. One of it acts as an oxidizing agent for flour and bread improvement, and we just talked about. Here adding a thiol group, thiolation. So again, chemical reaction where you add a compound that has a sulfur group, it reacts with the amine group of the protein, and then gives you a product that has a sulfide group to enhance potential disulfide interchange. So thiolation can also increase negative charge because it's reacting with an amine group. Another form of chemical modification is actually acid or alkaline reaction. We often use acid alkaline conditions when we are extracting the protein. So we do that. We often change the pH to enhance solubility, to enhance emulsification properties, or lower viscosity. So change the pH by adding acid or base. Sometimes the mild hydrolysis can occur, for example, changing of asparagine or glutamine to aspartic acid or glutamic acid. That will enhance the solubilization, solubility of the protein by adding a charge, for example, increase ionizable group. Sometimes, so this is what I meant by deamination or deamidation, that the asparagine loses an amine group and it becomes a carboxyl. What exposes the carboxyl. So you have C double bond O, when you lose an amine, then it becomes COO minus. So alkaline hydrolysis, however, or high alkalinity it is destructive to amino acid, and also at high pH, like pH above 10 or 11. That's why it's a challenge for Camelina and Chemicals, because we could be producing lots of alanine, which is biologically not available, and high level can be toxic. And these are glycosylation, phosphorylation, they're chemically induced. So you would add the chemicals to cause a covalent linkage with carbohydrates. So it's not the Maillard reaction. So glycosylation is different from Maillard induced glycation. So it's chemically induced. It's mostly it can happen with amine group, but it also can happen with OH group or SH group. It increases the net charge. Phosphorylation, you're adding a phosphate group, increase the net negative charge, and also potential binding, protein-protein interaction if we have the divalent ions. So can enhance, that's when enhanced gelation can happen, because we can enhance intermolecular interactions and formation of larger polymers. Okay, so moving into enzymatic modification. There are so many enzymatic modification. The enzymatic modification is actually a hydrolysis, like we said, formation of the curds in cheese, where you use chymosin, breaks down the glycomacropeptide and destabilize your casein micelles, so they form hydrophobic interaction, calcium phosphate bridges forming the curd. Meat tenderization is a hydrolysis process where you add to the meat. What do you add to the meat? Bromine, papain. Yeah, so what happens, it just hydrolyze a little bit the protein and kind of cause tenderness in your steak. Gluten modification, it's also a hydrolysis. You break down gluten into smaller molecules to make it less elastic if we're working with very strong or hard wheat flour. Production of hydrolysis, that means we're producing ingredients that are hydrolyzed, like whey protein hydrolysate, soy protein hydrolysate, pea protein hydrolysate, with the hope of enhanced functionality. Using determinase, which is an enzyme that deamidate glutamine in proteins, adding this negative charge, releasing ammonia, and that would cause the free of the carboxyl group, and then add negative charge. That enhances the solubility of the protein, and recently now we're trying to investigate the use of this enzyme to enhance the protein extraction yield. And then enzymes involved in cross-linking, such as transglutaminase, looking at ways to produce large molecular weight polymers, to enhance potentially texturization properties of the protein. Okay, so this is, oh, I forgot to animate. So this is the glutamine. With the enzyme glutaminase, we are deamidating or removing an amine group. And with that, we generate a carboxyl that it could be ionized. The transglutaminase, we already showed you it's the lysine and glutamine. The carboxyamide group of glutamine and the amine group of lysine, then we remove the amine group and cause a covalent interaction. Okay, so enzymatic modification in terms of use of to produce a protein hydrolysate. So this is in terms of an ingredient production, this is very, very common. It's used for a lot of different proteins. Whey protein is one, and it is used to enhance digestibility, for example, for baby formula. It is used to produce bioactive peptides that could have physiological benefits like antidepressants, antidepressant, promote satiety, etc. And also targeted improvement in functionality, improved solubility, like in hemp protein, six-fold improvement in solubility we were able to achieve, and other functional properties as well. Targeted enzymatic hydrolysis, though not random. So usually we target a degree of hydrolysis that is low, so that we don't get a lot of peptides that could potentially be bitter. So we increase the perception of bitterness at high percentage of degree of hydrolysis. Reduced allergenicity, yes, of course, hydrolysis reduces allergenicity, but in order to be completely hypoallergenic, you need to hydrolyze more than 50% of the peptides to ensure that all potential epitopes are disrupted. So when you do that, then the protein is not functional, the protein tastes bad, as sour, bitter, astringent, all of the above. So enzymatic hydrolysis is usually targeted. There's a lot of different enzymes you can choose from. So there are enzymes, we call them digestive enzymes, such as the trypsin and the pepsin and the chymotrypsin. And then there are proteases that from microbial origin that we can choose as well with different specificity. Some enzymes are very, very specific. They cut at specific regions. Other enzymes are called peptidases. They cut any peptide. And some enzymes are more exopeptidases or endopeptidases. If they are exo, they are leaving from the outside 1 or 2 amino acids or 3 amino acids. Endo, they go in and they chop anywhere. So depending on the enzymes we choose, their specificity, the environmental conditions, pH, temperature, time, even ionic strength, you're going to get a different set of peptides from the same protein. Same protein can result in different sets of peptides if we change these conditions. So some of these peptides can be bioactive, and the nature of these peptides can have different functionality. If we are releasing mostly hydrophobic peptides of larger molecular weight, then potentially we're enhancing the rich. If we are producing peptides that are more hydrophilic with increased charge, then we will enhance solubility. So depending on the enzyme conditions and the enzymes we can generate different protein or peptide profiles, we call it. And those different protein profiles will have very different characteristics. And here is just an old, very old diagram, but it kind of like illustrates that low degree of hydrolysis can be sufficient to produce bioactive peptide and not elicit a lot of bitterness. So this is the bitterness scale, this is the bioactivity scale. Increase the degree of hydrolysis, you might get very similar bioactivity, slightly higher and it plateaus over time. With more hydrolysis, you don't necessarily get better bioactivity, but you get a steep increase in bitterness. So we want to maintain low degree of hydrolysis, we can get good bioactivity and not so much bitterness, and hopefully potentially enhanced functionality. Yeah.
Yeah, no enzyme that can mask bitterness.
Yes, so there are debittering enzymes. So these debitter, but they don't mask, they debitter. And they act as mostly exopeptidases, and they chop off the sides, and sometimes they take off hydrophobic amino acids, so you would reduce the bitterness.
So you can be
They are currently used in industry, debittering enzymes, yeah. Yeah. We're actually using them in the lab as well. In our research. Exopeptidases. Okay, so enzymatic modification in comparison to chemical modification is targeted, it's more specific. Enzymes can be inactivated or can be immobilized, so they don't end up in your final product. And a lot of enzymes have GRAS status, generally recognized as safe. So they won't cause changes in amino acids, they won't reduce the nutritional quality of your ingredient. So in general, enzymatic modification is favored over chemical modification. So enzymatic hydrolysis, we should be controlled. And normally the way we control it is not only by the choice of the enzyme, but also by the degree of hydrolysis, also by the source of the protein. So here's an example of soy protein. So in this lane, there is soy protein, but the first lane here is soy protein. That's the only difference between this and this, they're flat. So this is soy protein, this is soy protein, but then on different gels, different sources of soy protein. So if here the protein that we used was for the hydrolysis was native protein, not wheat. Here the soy protein we used for the hydrolysis was already a commercial protein already made. So what happened is we use the same set of enzymes. We use terpene and pepsin. When we use terpene on this soy protein that was native, we see that, if you see at the top, I can't reach the top, beta conglycinin was clean. We don't see it anymore. We see the low molecular weight here. We see glycinin is still intact. So terpene was specific for beta conglycinin. Here we use pepsin. So pepsin was specific for glycine. It broke down glycine, we got low molecular weight peptide. Beta glycine was not touched. When we started with the denatured protein, there was no specificity. The specificity was lost. Protein was open and structured, the enzyme could reach multiple sites. We lost specificity. Why in this case specificity was important? Because if I want to enhance gelation, if I hydrolyze beta-glycine, I enhance gelation. If I hydrolyze glycine, I enhance emulsification. But if I start with an denatured protein, I'm not targeting anything. Everything gets hydrolyzed. You see a high degree of hydrolysis. Both terpene and pepsin are endoproteases. So they really chop everything, and you don't see, mostly you see low molecular weight proteins you lose functionality. Most functionality. So the gist of the story, in order to control hydrolysis and get to a target modification, we need to control what the starting protein is, what the state of the starting protein is, the nature, non-nature, what enzymes we use, what do we know about their specificity, and what degree of hydrolysis we're going to target. So there's and in order to control the degree of hydrolysis, we control obviously the time of the hydrolysis, but also the temperature and pH. We can adjust it. It is always recommended to work at optimum temperature and pH, but sometimes we change it a little bit, maybe we want it to be less than optimum, slightly less than optimum, so that we can control and limit the degree of hydrolysis. Okay, so that is, any questions here? Yes,
So what would be the purpose of the extensive hydrolysis?
here,
Uh-huh.
that is not, we don't want that to happen. So what happened here is something we don't want.
The reason that I asked, due to the research that I was doing, 12 sample was extensive hydrolyzed.
Yeah.
So even though it was commercial.
Yeah.
So what?
Okay, so the commercial was completely hydrolyzed, then it's bitter. Maybe it has better solubility, but then it's not gonna have bitter. Yeah. The problem with the hydrolysate that are in the market mostly bitterness. Yeah. This is research we've done, wow, 10 years ago. So here we utilize the ability to hydrolyze selectively certain components of soy food. And from previous research, when you hydrolyze beta from glycinin, you get better bioactivity, specifically antihypertensive activity. So we were looking at reducing the hydrolysate with enhanced antihypertensive activity. So a lot of the literature that we read is that they fractionate beta from glycinin from the flour. So imagine that it takes a lot to get the pure beta from glycinin instead of just getting the isolate. And they fractionate it, then they hydrolyze it, and then they produce the nutraceuticals, bioactive peptides that are hypertensive. From this work, we said we don't need to fractionate beta from glycine. How about we do targeted hydrolysis within the actual soy protein isolate, and then we can produce a hydrolysis with the same effect. So that was the objective of this work, and we said, okay, we're going to take soy protein isolate and we're going to get beta from glycine extraction. So we got the beta from glycine extraction, takes a lot of time to produce. And we got the glycine extraction, and again takes a long time to produce. And then we hydrolyzed both the SPI and the fraction with papain, and the SPI and the fraction with pepsin. And we tried to target similar degree of hydrolysis. So with the two enzymes, we achieved similar degree of hydrolysis for the isolate, similar degree of hydrolysis for the pepsin. Of course, it took a lot of work to get to there, so that's not the whole story. And then we determined the concentration at which we get 50% inhibition of a compound that induces hypertension, okay? Which is inhibition of the enzyme that leads to hypertension, enzyme in the body that leads to hypertension. So the concentration, the inhibition that happens, okay, the concentration causes 50% inhibition. That means the lower the number, the better is the potency, right? The lower this number, the higher is the potency. That means at lower concentration, we get 50% inhibition of the enzyme that causes hypertension. I'm trying to explain to you so that you know what these numbers are. Okay, so when we hydrolyze with papain and we hydrolyze beta-glycine, we have higher potency than when we hydrolyze glycine. Perfect, this is what the research has found. But what was interesting is that we found similar potency without the need to fraction it. So we used papain and we found that we don't need really to go through all the fractionation process if we do targeted hydrolysis within the non-fractionated isolate. So we got the same potency than using just fractionated sample. Of course, we proved with this gel that we targeted the correct peptides and we did proteomics. It was a very cool study 10 years ago. Yeah.
What was the reason using papain for beta-glycine and pepsin for elastin?
Okay, because papain targets beta-glycine, specific for yeah, especially if you start with non-denatured protein.
Okay.
So papain is an enzyme specific for beta-glycine, pepsin is specific for glycine. So we wanted to prove what literature had told us before that beta-glycine has more potency for inhibition. Yeah. Good. So what's the mechanism behind improved functionality? So when we hydrolyze, theoretically, we are releasing amine groups and carboxyl groups. So we have more ionization groups. So theoretically, when enhancing solubility, having more charge, we have more thermal stability because we have repulsion between the proteins, so we prevent polymerization. Improved gelation due to enhanced protein water interactions and probably enhanced balance of hydrophobic to hydrophilic or repulsive attractive forces. So enhancing surface activities. When you hydrolyze, it's also denatured. So you also open up the structure and expose different groups. So that's theory that with hydrolysis you can get this, but it has to be targeted, it has to be controlled so that you can get these activities. Do I have time or I'm done 5 minutes? Or are you guys tired?
A little tired.
Okay. Yeah, because I'm gonna get into another elaborate topic. I'll let you go. So next week we have 2 presentations, but I have to finish this lecture before we do the presentation. So we might potentially be a little bit later in time to finish. Okay, just be prepared for that. Okay.
Oh, I said I was.